Hello and welcome to another Tycho video. Today I am going to be talking about orbit determination for artificial satellites. And this can be thought of as two different components, the first of which is initial orbit determination. So you start with 2 or 3 observations of an object and you would like to have some rough idea as to its orbit. Now once you have collected additional observations on that same object, then you can make use of a technique known as differential correction. This allows you to refine that initial orbit. I also have a couple of examples to show both of these techniques in practice. So again, the goal here is to determine the orbit of an object. And once we have done that, we would also then like to generate what is known as a two-line element set for that object. And I will go into more detail on what a two-line element set is in just a moment. But one point of clarification is that throughout this video I am working with optical observations. Some might work with radar observations, but here we are just working with optical, and these are also known as angles-only measurements. So you have right ascension and declination. So a two-line element set, what does that look like? This can also be referred to sometimes as a three-line element set when you have the name of the object on line 0. So the orbital elements, these are on line 2. So you have inclination, right ascension of ascending node, eccentricity, argument of perigee, mean anomaly, and motion given in revolutions per day. So the idea here is once we have the orbit, we can generate this two-line element set. And this is very useful because it allows us to easily propagate the orbit forward and backward in time. In other words, we can specify a timestamp at which we would like to predict the position of that object. And so the propagator that is used with this is known as SGP4. It stands for Simplified General Perturbation version 4. And again, it allows us to predict where this object will be located at some given point in time. So again, I've mentioned initial orbit determination. This is where you have the first 2 or 3 observations of an object. So if you have just 2 observations, then it assumes a circular orbit. Now if you have a third observation, then it can make a minor adjustment to it to make a more educated guess as to the eccentricity. But again, this is just a very rough approximation, but the idea is that it is sufficient to hopefully recover the object in a short time span. So hopefully you can recover it on the same night and get additional observations. So once you have those additional observations, then you can make use of the technique known as differential correction, which again allows you to refine that initial orbit. And you can think of differential correction as a multi-dimensional Newton-Raphson approach to solving the problem. So what is Newton-Raphson? Well, a common example given is that you can use it to find the square root of 2, for example. So if you have x squared is equal to 2, then you can rearrange that equation to x squared minus 2. And again, the goal here is to find the root of the equation. So if you have x squared minus 2 is equal to 0, that's the idea. You want to find out what x is. And so Newton-Raphson formula, what that looks like is you have the current guess. This is x sub n. And you want to compute what the subsequent guess is supposed to be. And so you subtract out the current function value divided by the derivative at that same current guess. And this is a way to determine how much to change or adjust from your current guess. So again, working with that example, square root of 2, you might start with an initial guess of 1, and then you have 1.5, and then you go to 1.4167, and on the third iteration you have 1.4142. So this is an iterative process. So differential correction is similar, except we have multiple elements that we are trying to solve for. So the way it is set up is you have the residuals that you wish to minimize. In other words, you wish to find the root of this equation. You want to have ideally residuals of 0. So you have your observed value minus your computed value. So these are the observations minus the model, which is the essentially the orbit or the two-line element in this case, and it takes as input the elements of the orbit. So x in this case would, for example, be the semi-major axis, the eccentricity, inclination, rate ascension of ascending node, argument of perigee, and mean anomaly. Now, with the two-line element set, we do not have semi-major axis. Instead, we have mean motion, which is revolutions per day. So that's a minor adjustment there. And also a further twist to it is that numerically, we do not like to deal with these classical elements. Reason for that is that you have what's called singularities. So if the inclination is 0, then the right ascension of ascending node is not well defined. And similarly, if the eccentricity is 0, then the argument of perigee is also not well defined. So we then like to convert from classical elements to what are known as equinoctial elements for the numerical evaluation. Now, you do not really have to concern yourself with this, but this is just something to think about if you are interested in how it works under the hood. But this is the workflow diagram here, and I have this from a 2008 publication. So the idea is, again, you start with the initial orbit, and you loop through the observations, and for each observation you have the timestamp, and you therefore try to predict where that object would be using the current model. So you do this for each of the observations, and you compute the residuals and solve the Jacobian. This is the partial derivatives of the elements with respect to the observations. Solve the least squares, and then you ask the question, has it converged? So you have an epsilon, which determines the tolerance. So at what point do we decide that we are satisfied with the current solution? Now, another thing to keep in mind is that for orbit determination, it's very critical to have proper spacing of the observations. So this shows you 3 different scenarios here. So the first scenario is proper spacing, where you have observation at T1, observation at T2, and an observation at T3. So this would be an ideal spacing of the measurements. Here we have an example of improper spacing. These two are too close together, and then you have this third one here. And finally, another example, again, improperly spaced, where the first two are acceptable. You have T1 and T2, but then that third observation is too far apart. And so this is multi-revolution data. The time span is too far apart. So again, keep that in mind, that when you're dealing with this in practice, you want your measurements to be properly spaced apart. So now let's go ahead and take a look at these 2 examples here. One, I have a circular orbit, and the other has high eccentricity. Okay, so this first example is ACS3, which is the Advanced Composite Solar Cell System. And this is an object in low Earth orbit. It has a very circular orbit as well. So I've captured 3 data sets, 3 sequences of images on this object. So let's go ahead and start with the first data set here. I go to List, Add Images. And as you can see, there are 171 images in this set. They're each 0.3 seconds in duration. So the total time is 51 seconds for this first set of images. So what I can do is go to Action, Fast Tracker, and what this is going to allow for me to do is to very easily determine where in this set of images the object occurs. So here it has returned with the result. It has identified one object, and we can do File Match ArtSats to identify this detection with known artificial satellites. So as you can see, it has identified this detection here as being ACS3. So when I click on this result, you can see this is the detection here, and we wish to measure this object to try to compute an initial orbit. So if I want to, I can say, okay, this is detected on image 92, and if I want to do a comprehensive set of 3 images for this first data set, I can go back a few images to get the initial detection here. And I right-click, create ruler, and then place a start and stop point on the streak. And I go to the midpoint and right-click and choose Create Observation. So I have now measured the midpoint of the streak of this object. So that is the first measurement. And now I can create 2 additional measurements of this object. So here will be the second measurement here. And finally, a third measurement. Okay, so now we have 3 measurements, and what I would like to do before continuing is I can go ahead and right-click on the identification here and choose Add to TLE Propagator. And so what you'll notice is we now have the TLE of the object, the actual reference set of elements. So this will be, if you will, the truth data. And what we want to do now is compare our initial orbit to that truth data. So I have these 3 measurements here. I can choose Add to Target List, and then I can choose Report, Generate IOD Report. So what this does is it generates a report in the IOD format, and once you have that, then you can make use of these additional features, such as generating an initial TLE or refining an existing TLE. So if I have just 2 measurements, again, it will assume that it is a circular orbit. So I can go to TLE Analysis, Generate Initial TLE, and you can see that it actually does a pretty decent job because, again, this is actually an object with a circular orbit. Now, if I supplied all 3 measurements and requested initial TLE on that, you can see that it actually, it is still reasonable, but it could be better. So if we look at the comparison of the first 2, this is what that looks like. So it's a very close match with the actual reference TLE. So that's actually pretty good. And if I compare the first and third orbits here, you can see that there's a little bit of a difference. So it's not quite as good a match as if I had just used the first 2, or just for if I had just used 2 rather than 3 observations. So that would be one scenario where actually an additional observation, especially since it is so close in time, it might not be advantageous for that initial orbit determination. But I will be showing in the second example a case where having 3 measurements is certainly useful. So now we have our initial orbit. Let's go ahead and generate additional measurements to refine the orbit further. Okay, so these are the 9 observations generated from all 3 data sets on this object. So what we can do next is to make use of the differential correction routine. So to do that, we go to TLE Analysis, Refine Existing TLE, which presents a new window here, and it takes as input an existing TLE. So to demonstrate this more clearly, I will make use of the suboptimal orbit that was generated here. So I can right click and choose Show TLE Text, and then I can copy that into this window here. So what we are saying is that we want to improve upon this orbit using all of these observations. So I click the Start button here, and as you can see, it has completed that routine. So it started with an error of 0.05 and completed with an error of 0.006. Now I can copy the result to the TLE propagator, and you see this orbit here. So let's go ahead and compare again the first and the third. As you see here, this is what that looks like. So what we are saying is that we hope we have improved on that initial orbit. So now if I compare the first and last, we should see an improvement. And indeed, they have a much closer agreement with that refinement. So that is the first example. Now let's take a look at an object having higher eccentricity. Okay, so to keep this video short, I have already generated the observations for this object. So I can proceed to navigate to the Satellites menu, choose Observations, and paste the observations into this window. And as before, we would like to demonstrate both the initial orbit determination process as well as the differential correction routine. And again, with initial orbit determination, that takes in either 2 or 3 observations. And I would also like to highlight the importance of having sufficient time span on an object, especially of this nature that has higher eccentricity and is in a higher altitude. So I'm going to demonstrate two different scenarios, the first of which will have a time span of 8 minutes, and the second of which will have a time span of 1 hour 10 minutes. So let's go ahead and start with the first scenario. I'm going to delete all but the first 3 observations. And if you are familiar with the IOD format, then you might recognize that this is the hour column and this is the minute column. So the first observation starts at 0856 and the last observation ends at 0904. In other words, this is approximately 8 minutes of time on this object. So let's go ahead and generate an initial orbit using these 3 observations. I go to TLE analysis, generate initial TLE, and you can see this is the computed result. Now let's also take a look at what would happen if I just supplied it with 2 observations. So I delete the one in the middle, and you can see what that looks like here. This is the result. So again, with 2 observations, it assumes a circular orbit, and we can see that here when I select both orbits and attach to the satellite viewer, and I zoom out a bit here. And because this is in a higher altitude, I have to choose a longer duration than 90 minutes. So either 24 hours or 72 and replot. So you can see what that looks like here. The green orbit is the circular orbit derived from just 2 observations, and the yellow orbit is the one derived from 3 observations. So now let's compare that orbit from the 3 observations with the actual true orbit of the object, and we can see what that looks like here. And you can see that this is not terrible, but we could certainly do a much better job than that. We can strive to have them be in much closer agreement. So now let's go to scenario number 2, where I have a time span of 1 hour 10 minutes as opposed to just 8 minutes on the object. So I'm going to choose the first observation, the one in the middle, and the last observation. So I will delete all the other observations and choose and generate initial TLE. And now we see that if I compare the first and last orbit here, what that looks like, they are now in very good agreement with each other. So this highlights the importance of having sufficient time span on the object. So this is initial orbit determination on this type of object. Now let's take a look at differential correction. So what I'm going to do is restore all of the observations on this object. And let's suppose that we had the suboptimal orbit here of the 2.57 revolutions per day. So I show the TLE text, and what I'm going to do is supply this as an input to the differential correction routine. So I go to TLE analysis, refine existing TLE, and I can paste that orbit into this window here. And again, it is going to make use of all of these observations to refine this orbit. So I click Start, and you can see we started at an error of 0.12, and we ended at an error of 0.0004. So I can copy that result to the TLE propagator and compare it with that true orbit. And you can see that this is the result here. So it went from this kind of comparison here, and with differential correction, it was able to improve it to be in much closer agreement to the actual orbit. Now, differential correction itself is not magic. It will not take a very poor initial guess and improve it. Differential correction, because it relies on an iterative process that assumes you have an initial guess that is valid, it can also get stuck in what are called local minima. So what can occur there is it starts to improve the orbit, and then it reaches a point where it thinks that it has achieved a global minimum when in fact it is just a local minimum. So again, you have to be aware of the nuances of these certain numerical iterations. But let me demonstrate that here. So if we were to take the circular orbit, we could try to apply differential correction to that and see what happens. So this is the circular orbit, which is certainly not a match for the actual orbit of the object. So if we try to refine that, what happens? So I paste that into the existing TLE window, and I can reset the output here, and click Start, and you can see that it really made very little difference. We started with an error of 1.6 and ended with 1.6. So revolutions per day stayed pretty much the same at 1.04. So if I try to compare the two orbits here, you can see that there's very little change. It's still a very circular orbit. So differential correction is not going to magically improve an orbit that is so far apart from the actual orbit of the object. So keep that in mind. It's not going to just magically compute an orbit from scratch. It relies upon having a good initial guess. So that is about it for this video. I want to thank you for watching and see you next time.